Guys, just trying out some new software today, so we'll see how this works. So you'll see a little picture of me here. I know how much you miss me, so I thought I'd give this a try. So for our next unit, it's called motion, and what we're going to be doing in this unit is sort of looking at how objects move and what are the laws that dictate how they move, what the forces are that cause them to move. And so we're going to start today with just a discussion of speed and acceleration. We're going to define some terms. We'll learn how to calculate the speed of an object, the acceleration of an object. We'll look at some graphs that show the movement of an object. And then you'll have some practice to do with those things. So let's start with some definitions. So when we talk about the speed of an object, the definition of speed is the distance that object travels divided by the time that it took for it to travel that distance. It sort of is common sense. Okay? If it takes you less time to travel a certain distance, your speed is greater. So if you go out to the track looking to get some exercise and you run 400 meters and it takes you 1 minute and 30 seconds, you would be running faster than if it took you 2 minutes. So to calculate the speed of an object, we have a formula. It's just very simple. The distance over the time it took. Okay? We'll often abbreviate distance as d and time as t. So if I look at an example here, if I have a bird that travels 100 kilometers in 5 hours, what is its average speed? So just like we did for our other units when we were solving problems and calculating things, we're going to use the same pattern. We're going to write down the formula first. We're going to substitute in our variables, and then we'll finish with an answer including units. So the bird travels 100 kilometers in 5 hours. Substitute in our variables. The distance is 100 kilometers. The time it took for it to fly that distance was 5 hours. And we do our math to get an answer of 20 kilometers per hour. So 100 divided by 5 is 20. Remember, what we do with our numbers, we also do with our units. So that's where we get kilometers per hour. Okay? If here we had different units, then our units in the final answer would be different. Again, what you'll also notice here, I'm talking about average speed. You know, if we think about real life, a bird can't fly exactly at a constant speed of 20 kilometers per hour. Okay? And so when we talk about distance versus divided by time, we're talking about the average speed over that period of time. So like, for example, if you were going to drive from Utica, New York to Myrtle Beach, South Carolina, okay, you might know the overall distance and how long it took you to drive, but you're going to be speeding up within there, slowing down. You might stop for lunch. So what we are actually calculating is the average speed. So let's do another problem. In 30 minutes, a rocket traveled 1,400 meters. What is its average speed? So take a minute and you solve this problem, and you can pause the video, and then we'll come back and just be sure that you know how to do this. So again, I'd like you to start with your formula. Speed equals distance over time. Substitute in your variables. The distance in this case is 1,400 meters. The time is 30 minutes. Do our math. And get our answer of 46.7 meters per minute. And pay attention to your units here. Make sure you get them correct. And so sometimes as we are moving forward here in our notes, we're going to be talking about constant speed. And this sort of goes with what I was just talking about. Constant speed is if an object is traveling at the same speed consistently for a period of time. Now in real life, this doesn't often happen. Okay. To reach a certain speed, you need to speed up. Okay. Eventually to stop, you need to slow down. There's variation during that time. But for our purposes, we're often going to assume objects are traveling at a constant speed. Now, if you know anything about your parents' car, you know that you can set a button that's called the cruise control. And the cruise control button will attempt to keep the car's speed constant, okay, without the driver having to use the accelerator or the brakes. Now, when we talk about velocity, in sort of our everyday language, we might use these terms kind of interchangeably, but there technically is a difference. When it comes to physics, when we're talking about the velocity of an object, it's not quite the same as speed. Velocity includes both the speed that the object is traveling, but also includes a direction. Okay, so if we're asking for velocity, technically, we should be writing down both speed, so we have here 50 kilometers per hour, and a direction. So if this boat's traveling 50 kilometers per hour south, that's a velocity. So what happens if this boat, I guess I have a spelling error, bolt, changes course and heads east? Still maintaining 50 kilometers per hour. Has its velocity changed? And the answer that's yes. Okay, if the direction changes, then the velocity changes. Its new velocity will be 50 kilometers per hour east. So when we talk about velocity and we're trying to understand it, some interesting things. If you think about if you've ever been in a big airport where they have sort of those moving walkways, if you're on that moving walkway and you're also walking forward at the same time, when you look off to the side, to people that are not on that walkway or to the wall, it seems like you're moving very quickly, even though you're sort of walking at your normal pace. This is because to look at your overall velocity compared to people not on that walkway, not only are you moving forward with the speed with which you're walking, but you also have to add on the speed of that moving walkway. If you imagine a man's on a train and it's moving 200 kilometers per hour due west, if that man also is walking forward through the train at a speed of 5 kilometers per hour, what's that man's overall velocity compared to outside of the train? If you were looking out the window, you'd see things going by at an overall speed of train moving 200 kilometers per hour. He's also moving on that train an additional 5 kilometers per hour. So overall, that man's moving at 205 kilometers per hour. That man's coming back and moving back to his seat, he's walking the opposite direction of the train. What does overall velocity be in that situation? Okay, we'd have to subtract the velocities, because since the man is walking the opposite direction of the train, he'd be moving still in the same direction, due west, 195 kilometers per hour. So I mentioned a little bit about acceleration. That acceleration is when there's a change in speed over time. Okay. And so to calculate the acceleration of an object, we need some information. Okay. So our definition is going to be a change in the velocity of an object over a period of time. The formula for us to calculate acceleration change in the velocity of the object divided by the time it took to change velocity. So you'll see here I have some symbols that we often will use. So to figure out the change in velocity, we take the final velocity of the object once it has reached the end speed, subtract the initial or starting velocity, so we have VF minus VI divided by time. So let's look at that. It'll make a little bit more sense if we see it applied to a few problems. So if a rocket accelerates from 0 to 20 kilometers per second in 10 seconds, what is the acceleration of that rocket? So we'll set up our formula. Acceleration equals VF minus VI divided by t. Final velocity minus initial velocity, do that subtraction, and then divide it by the time it took. In this case, it's pretty simple. The final velocity, what would it be? It's 20 kilometers per second. Its initial velocity was 0 kilometers per second. And the time it took was 10 seconds. 20 kilometers per second minus 0 kilometers per second divided by 10 seconds. Do my math. 20 minus 0 is 20. Divided by 10 is 2. And again, our units are important. So here, the units are kilometers per second, and then we also are dividing again per second. And so if we really think about what units mean, it means that for every second that was going by, this rocket was accelerating 2 kilometers per second. And that's where we get 2 kilometers per second per second. Now there's another way of showing this. Sometimes you'll see this shown as 2 kilometers per second squared. Okay, so it's another way of showing kilometers per second per second. Let's do another example. Let's have you do this example. Okay. So a person on a motorcycle accelerates from 7 kilometers per hour to 37 kilometers per hour. It took 2 minutes to make that change. What was her acceleration? Why don't you go ahead, solve this problem, follow all the steps, pause the video, and then I'll explain. Okay, so again, we want to start with our formula. Acceleration equals VF minus VI over time. In this case, the final velocity, the ending velocity, was 37 kilometers per hour. The initial or starting velocity was 7 kilometers per hour. And the time was 2 minutes. So we set up our problem. We do the math. 37 minus 7 is 30. Divided by 2 is 15. What about units here? Careful with the units. So remember what we do with our numbers, we do with our units. So here we have kilometers per second per minute. So think about what this means. Every minute that went by, this motorcycle accelerated 15 kilometers per second. Those should have been hours. I apologize. I made a mistake. So this should be hours, hours, hours. So actually it should be 15 kilometers per hour per minute. Now, is it possible for acceleration to ever be negative? Think about that for a minute. Yes, it is. So when would acceleration be negative? If an object's slowing down. If an object's decreasing speed, or we might call that decelerating, the acceleration will come out to be a negative number because your final velocity is going to be less than your initial starting velocity. That's deceleration. We'll show that to be negative. So often when we're trying to show an object moving over time, we're going to use some graphs to do that. And I'll explain these graphs here. So there's two different types of graphs we might use. One is a distance versus time graph, and one is a velocity versus time graph. We'll start with distance versus time. So in these graphs, we have time on the x-axis, and then we have distance on the y-axis. This is distance is sort of from the starting point as this object's moving. So if you look at this graph here, so as time is moving forward, the distance this object is from the starting point is increasing. It's getting farther away. Then let's think about what's happening here at B. So now as time is moving on, this object, its distance from its starting point is not changing. That would mean it stopped moving. In this section of the graph, as time's moving on, this object is going back towards its starting point. It's returning. So when we look at these graphs of distance versus time, the slope of a line, if the line has a consistent slope like this, if it's a straight line, okay, that represents the object moving at a constant speed. This plateau represents no movement at all. The object is stopped. And the steeper the slope of this line is, think about what does that mean? A steep slope means in a short period of time, the object is traveling a farther distance. What does that mean? It means the steeper the slope, the faster the speed of the object. If we imagine a slope that's very gradual, okay, over this long period of time, if there were a line there, its distance is not changing very quickly. That would be a slower speed. Okay, let's look at this graph down here. Can I move myself? Oh yeah, I can. Interesting. So here we have another graph of distance. This time it's in meters divided by time. So think about what's going on with this graph. So what is this showing? What's happening to this object? Think about that for a second. So during this first part of the graph, the object's moving at a constant speed. Again, it's a straight line. But then as we get to this section of the graph, the line is curving and what's starting to happen to it? It's getting steeper. Okay. So here we have an object moving at a constant speed. For a while the line curves and gets steeper, and then it continues at the steeper slope. So this graph shows acceleration in this area. It went from a slower speed to a faster speed. Okay, the object's speeding up. Okay, what about this graph? We have a steep line, a less steep line, and then that curve in between. That's an object that's decelerating. It's slowing down. So what I'd like you to do here is to draw in your own graph of a biker that's accelerating from a red light, and then she reaches a constant speed. Draw that graph on this set of axes you have over here. Pause the video. So if the biker is at a red light and then accelerates to reach a constant speed, okay, we have our initial start, this line curving up, but when she reaches a constant speed, that line then straightens out. Hopefully your graph looks similar to that. Okay. To finish up, we're going to talk about a different type of graph. Now, if you look at the axes here, this graph's showing something different. We again have time on the x-axis, but on the y-axis, what do we have? We have velocity, or it might be shown as speed. So this graph shows something a little different. And what these lines represent is different on a velocity versus time graph versus the distance versus time graphs that we were just looking at. And that should make sense if you really think about what's going on here in this graph. Okay, so this shows the speed of a boat over a period of 16 minutes. This velocity is in meters per second. So think about what's happening here. So at the very beginning, and this is minute 0, in the first couple minutes, what's going on? Well, the line is increasing. So what does that mean? Well, it means the velocity is increasing for the first 2 minutes. Okay, then that means it's accelerating. Its velocity is increasing. And what does this part of the line mean? So now the velocity is staying constant at 8 meters per second for a while. It's moving at a constant speed. What does this represent here? The object is decelerating. It's slowing down. And then here, again, it's traveling at a constant speed. On these graphs, the slope of the line represents acceleration. The steeper the slope, the faster the object was accelerating. And that makes sense. Okay, if we had a gradual line here, it would mean the velocity is increasing, but it's happening over a longer period of time. It's slower acceleration. So let's look at this graph and we can answer a few questions about it. So what was the boat's speed? We're talking here about average speed between 2 to 10 minutes. So we have to look at our graph between 2 and 10 minutes. Well, I'm using speed and velocity interchangeably here, by the way. During that time, the speed was constant. It was constantly moving at a speed of 8 meters per second. Was the speed constant? Yes, because the line was flat. The velocity was not changing during that time period. Okay, we could also look at this graph and we can calculate the acceleration of this boat. So what was the boat's acceleration from minutes 0 to 8 minutes? So 0 to 8 minutes. Okay, we want to show our work here. So let's write our formula. Acceleration equals Vf minus Vi over t. Final velocity minus initial velocity over time. So Vf, what was its final velocity? Well, we have to look at 8 minutes. 8 minutes, its final velocity was 8 meters per second. What was its initial starting velocity at 0? At 0, it was 0. So if final velocity is 8 meters per second, initial velocity is 0 meters per second. The time it took, so 0 to 8 minutes, that's 8 minutes. That's our answer. 8 minus 0 divided by 8 is 1 meter per second per minute. Okay, what was the boat's velocity at 8 minutes? If we go up here, follow our graph over, its velocity was 8 meters per second. Then the last question, between what time intervals was acceleration the greatest? So when was this accelerating at the highest rate? Well, between 0 and 2 minutes. Okay, and how do we know that? Because that's when the graph was steepest. Okay, so that's the end of our notes for today. So just to help you be sure you understand this, when you're looking at these graphs, you always really want to pay attention to the axes. So say, what is this graph showing us? Is this graph showing us velocity over time, speed over time, or is it showing us distance over time? Because obviously, the shape of the graph means something different if it's a graph of speed versus time or if it's a graph versus distance over time. So you just have to think about it. Think about what this graph, what this data really means, and it will help you to understand what's happening in this graph. Okay, so that's our notes for today. You'll be doing some practice with these problems and graphs the next couple days, and then we'll come back and we'll do some of our notes about Newton's laws. So I hope you have a great day.